Kao što vidite, imali smo malo više hardvera za naštimati i spojiti.
Aha.
Tako da sad ponovo predstavljamo Davora i...
Hello.
Davor,
Hello everybody. I'm just connecting. I would like to present you some work about simple but, let's say, efficient video accelerator for the open source hardware, which was developed actually on this faculty about 7 years ago. Marko Zec wanted to teach digital logic, and he introduced FPGA development board chips, which he himself designed here as a learning platform. So it could be bought in the paper shop at the faculty, and people could use it as lectures, but also they could make it something on their own. What's it about? It's actually the technology which is something between the software and the hardware. It's FPGA. This is a programmable field programmable gate array chips. So these chips are in effect something that can accept software as a code, but inside of a chip, digital logic reconnects itself so that it creates a circuit. Digital circuit which works like normal circuit made from the parts. So at the table you don't need any soldering iron or something like that. You just need the skills of interface, which is a programming language called VHDL. So well, what can we? This is somehow. How does it work? This is simplified layout of the chip. It's, as you see, array, which on the array there are memory blocks which memorize what the user wants to reconnect. Do you want to reconnect things horizontal, vertical, on a side? So this is one of the connection logic block simplified, which is only programmed. Of course, you are not programming each logic individually. You are using a language called VHDL, and some complex software tool does it for you. It is not impossible that you can explicitly connect some gates. It can be worked also at that way, but you know, it would be a little bit difficult to make a processor like that. So this is a hardware which we had, which actually Marko had designed, and we at Radiona bought one of these, and my personally I was surprised how big and how packed is it with the features. It has RAM, it has software for the SD card, flash interfaces. You can connect audio, video, some buttons and LED stuff. So I asked Marko, would you be so kind and make it open source? And he said, yes, of course, I was a long time making to do it. In fact, it appeared that he already had designed soft-core microprocessor, MIPS compatible. It is not used as at the course of the teaching. It would be too complex, but he wanted to see does it work and how does it perform. Comparing to some other processors that I know, this soft-core processor has two good features. It was small. In terms of FPGA, you don't have so much silicon resources to use. So you need to be sparse when you are spending some kind of blocks, memories, whatever inside is available from the manufacturer. It was small and it was fast. It is faster than ARM CPU of the similar class. So I mean some ARMs like STM32 or something that's running about 100 megahertz, which is also the clock of this processor. So it's more efficient than ARM. It is nice. It has even some kind. It had actually some years ago some basic SoC, system of a chip. Let me. So I'm only advertising a little bit more. So it has basic audio, video, done like a soft core. So everything is like a kind of processor. It didn't have acceleration, and it was missing some kind of extra features like HDMI output or maybe some advanced timer and so on. So me at Radiona decided, let's do it. Let's make some extra stuff for this. This processor is super. It is open source. At the same time, when it was released as open source, we also released the Arduino support for that. So Arduino environment with complete GCC and everything is available for that. Now we worked a little bit more on that and make it also portable. So it doesn't work only on our hardware. It has about 20 or something boards different, which we tested that it works. We try to be as portable as possible, so it will be not a big deal if somebody sends us, for example, hardware and say, let me make support for my hardware. I think it's question of at once for 1 week or something to get a new support. So for example, one kind person from Kiev sent me one board. Actually, I asked him, would you send me your board if I, for return, make a support for this? And he said, yes, of course, I would. And then immediately he agreed on mail. And I said, yes, super, let's make a support. Let's start it right now. Already I don't have a board, but I have schematics of his board. So I did the support few days before the board was actually shipped, and I sent him the bitstream. This is a connection logic. And so let's him, oh man, can you try this bitstream on your board? I didn't yet receive yours. Let's see, will it work? And he said it works. So a few days ago, I get the board, and obviously, even on my board, it worked. So this is let me say, in particular, we are actually dealing here with the video accelerator hardware. So video accelerator hardware done in VHDL it's some hardware done in software. It looks like a code. It has lines. It has a text file which are only lines. You can do it with a text editor. But in this code, to program something, you need to switch your logic. If you are familiar with procedural languages like, I don't know, C, Python, and stuff like this, all of these languages have something in common. This is program counter. So execution of each line is sequential. One line by line is executed in the sequence order. Okay, it can be loops, it can be jumps, but only there is one single execution point. In the FPGA, everything is parallel, so each line which you write is constantly being executed. This is a switch in the logic if you are making hardware from the software point of view. I think it's a good point to start. Change your thinking first, and then try to make some circuit or project. It will be really hard if you try to make it sequentially, if you do it your own way of programming. It could be possible. Compilers are so good that even if you write sequential code, that they will compile it, but you will quickly run out of the hardware resources. What does this video do here? We call it Compositing 2, because Compositing 1 existed, but it was a little bit lousy. So me and Marco sit one day and said, what can we do about this video? And it was quickly scratched. We need acceleration of stuff like two-dimensional objects, which can have either transparency, so imagine a Pac-Man chasing a ghost, and then Pac-Man eats the ghost. So Pac-Man has a mouth which is transparent. When displayed, we need that one object can have priority over the other object, but in two-dimensional space. However, it does a certain amount of illusion. So we have a 2D, which is actually 2.5D, because we have object with priority. When it moves, you can have a sort of three-dimensional illusion. This is I can say used in 80s games like arcade games. Pac-Man is Tetris and games like this. It's not quite free arena, but you know what I mean. How does this video accelerator actually accelerate stuff? Because we have a small processor. It is much less efficient than Intel, which runs of gigahertz. We have some megahertz, okay. We don't try to compete with Intel, of course. But still, we don't want that video to be lousy. If we have ordinary video, like frame buffer, which you are probably familiar with, this is some kind of a continuous frame of lines which are represented in the memory like bytes. So continuously you can fill bytes in the first line, then you fill second, and so on until the full screen. If you want to update something which is animated, then on the full screen and such processor like 100 megahertz F32C, you will have problems. You will have problems with the memory bandwidth, and things will run slowly. You will see things drawn on the screen. You don't want to see that. You won't see the flash when something is changing or some animation goes. We decided to make some kind of intervention in the way we are displaying data. We wanted to have backwards compatibility with the old code. So if we need a frame buffer, we want to still have it as a special case. But then we also wanted to have some kind of a structure similar to the linked list we are familiar in the normal computing. If we relink something on the linked list, we will have some changes, some quick changes on the screen with very little intervention in changes of the RAM content. And this is actually what it does. It is a vertical scanline list of no numbers of lines. For example, we have 640 lines horizontally and 480 vertically in VGA classically. So only we memorize continuously 480 vertical lines as a series of pointers to the color content, which can jump over content on the screen which is not shown. Only what has a content will be displayed. And the sprites, which are two-dimensional objects we want to animate, are actually consist as a series of multiple horizontal lines. So each individual sprite in his reduced sense is a tiny horizontal line. A collection of, I don't know, 20, 40,000 of them in vertical sense make an object that people perceive as two-dimensional visible object on the screen. Relinking on the list and shifting them horizontally. Horizontal shift can be easy. You just change the X vector, X address of some content, and it immediately jumps on the other. No changing of the RAM content, no moving of the whole bitmap is necessary to move either it horizontally and also vertically. You just relink it on the other parts of the screen. This is in the C programming languages representation of the data, which does all of that. So it's quite simple. It has 480, we call it vertical lines, scan line. This is these things above, see? And these stages, 0, 1, 2, 3, and 4, are hardware finite state machine stages that we want to interpret this structure. So basically, we first designed C structure of the C programming languages that efficiently can match something that hardware can interpret. Our hardware will also interpret this structure directly into memory without any intervention of the processor. And 5 stages are 5 RAM cycles that RAM fetches 32 bits of the memory inside of its register. First fetch, we will see, is there any content of the line? If there is a null, not null, we have something to show. Then go stage 1. We will fetch, do we have another content after this content? If this is null, this will be the last content shown. This is the exposition of the content. So horizontally, where to show this content, how many pixels does it have. This stage 2 is 32 bits fetched at once. This is a pointer to the actual content, so we can reuse the content. If we have same sprite 1,000 times shown on the screen, we will memorize it only once and show only the copies. It will be done automatically. And stage 4 is, of course, fetching, pixel by pixel and showing them. This is a main snippet of the VHDL accelerator. As you can see, it is a programming languages, but you must think it as the hardware. All of these stages are hardware that is present at the same time, and there is a switching logic, some kind of a counter that counts from 1, 2, 3, 4, and 5. It switches which part of the hardware will be active at one of the stage. So what I seen on this picture, C++, this is a core code of the video accelerator that interprets it in the hardware. And this is finally, you know, if you want to move some sprite or something, actually we need to also some kind of a C code that remaps and relinks the screen. And here is a small procedure. I mean, after each change of the sprite, or of many sprites, whatever, we need to call list relinking. And this is some kind of trade-off, you know. We are also saving the silicon units in our chips. And this help of the normal processing logic is good trade-off that we can quickly update the screen, and the processor doesn't have too much work to do. It will not copy any large memory blocks, any something. It will just relink the pointers. So what we need to do, we want to move sprite something right, change X. We want to sprite move to vertically, change Y. Okay, this Y, there is some code upstairs that makes Y clipping. A sprite can be 2 down on the screen or 2 up or halfway near the edge of the screen. So I'm not showing some simple code away, but this is the main code which does it. So it's not too big as well. I can have some before the conclusion and showing you the real hardware. So in this feature, we can have overlapping sprites. We can also accelerate classical windows, which we can have on desktop computers. We can do animation too. In the memory, we can have many parts of the content of different pictures during the animation. And just shifting the BMP pointer to the another frame, we will make animation also very easy in the CPU cycles. It is small in the silicon. Everything what we see on the screen is still in the CPU RAM. We don't have some kind of external RAM like a video card, like, I don't know, NVIDIA and these things. We are sharing the RAM with the CPU. This is the only RAM usually available on the FPGA boards. We can reuse the content. So one sprite can be memorized once on the memory and show many times. We have bandwidth throttling. Of course, if we make a long list with too much content, the RAM will not be able to handle them all. But we designed a feature because we have vertical lines of the list and we have strict timing of the RAM. We cannot wait for the screen. Screen doesn't wait, you know. It wants to fetch new data. When the data are needed to be shown on the screen, exactly on that time, hardware must output colors. If the hardware cannot output the colors, it will skip lines. So lines will get rarefied. I will show you on the example. This is bandwidth throttling. So not the whole screen will be destroyed and invisible, but only the parts which cannot be fetched will not be seen. I can say it in my experience that if you have some quick action with animation and so on, about 10 or 20% can be out of bandwidth, but the people still not will notice it. So you will see that everything is right on the screen, but 50% of the pixel will be missing. I will show it to you also. I can see where to look. It's very good for a video acceleration of some simple hardware and stuff like we have. Okay, we departed from the frame buffer, but we can still have it as a special case. And okay, inside this is some kind of a technical stuff. I will then, or maybe say, let's say now, connect it, disconnect this presentation, don't be afraid, and connect it to our FPGA chip. Yeah, let me see, will it sync? Okay, this is a test screen, and on my computer I have Arduino environment. So let me check some kind of a simple, I make some kind of simple games which do the animation. Yeah, so this is the simplest which we have. We have compositing accelerator, memorizing only very few parts of the colors. So we are memorizing only one single scan line of this. We have how can I say, orange line and white line. Everything else is just moving of the pointers. So you see like something is drawn on the screen and nothing is drawn here. Only the pointers are changing. And this is what you actually see like animation. Let's see some other example. I will show you the bandwidth throttling. I will make a font of the sprites, which is actually not the way it should be done, but it will be obvious when the throttling does, and how does it look like. So when it is too much vertical sprites and content, so the RAM cannot handle them all, it will rarefy the lines. But still something will be seen. If there is an animation, okay, of course you cannot overdo it. There is some kind of limit. But it will allow you to use the hardware as much as possible. I have, for example, one thing for the Windows acceleration. So sprites, like objects, two-dimensional, can be really large. It can be large as a whole screen of some great portion of it. This is one of the example. So also this is not moving any content in RAM. It will be not possible. This is a 32 BPP, and a processor like this one cannot do it normally by changing the blocks, and especially it cannot handle the transparency when something is behind of something. It will need to clear one whole RAM in the other invisible, make it, and it will really be slow. We can wait maybe a few seconds for an update, but this is updating. And as the finally maybe nicest for us to see, This is some kind of preview of some hypothetical game that uses much acceleration with many sprites. So this is a part. These sprites are intentionally drawn ugly like that, but they can have each pixel defined. You know, this is just for a demonstration. So we could have a nice graphic here, no problem, but somebody needs to pixelize it. So I invite you, if there is some kind of artists, you can help us. So this is how it works and how it looks like. Can I see or hear some questions? Any question? I heard something. Silence. It's impossible, but yeah. You are looking at the animation. Yeah. Yeah, who knows what will happen? Will it work for the next? Yeah, it works. Do you want to see something else? Let's see. I have another one. Just let's see here. Because I was talking about many sprites and I forgot to show them. So this is some kind of a many of them. So somewhere on the top there will be throttling on the bandwidth. Some sprite will be in this horizontal area partially shown, but you must really pay attention of that, otherwise you will think everything is all right on the screen. Yeah? Mm-hmm. All this, no, much more or less, maybe 100 bytes. So one data is white ship, second data is orange ship, and third data is green ship. This is the old data in the memory, okay, not counting the pointers, but this is the old content data, so maybe 100 pixels at most, maybe 200, I don't know, some kind of 200 pixels time 4 bytes. Yeah, it could be 1 kilobyte because we have true color of that. This is the old data of the RAM content which is shown here on this screen. Yes, that's right. We completely don't need large RAM. So this display, if it had a real frame buffer, would take megabyte or something. But we can handle with 1 kilobyte. We can fill the screen with 1 kilobyte with some gadget, widgets, or whatever, if we reuse the content with the sprites, without any large RAM. And we will have also the bandwidth saving for the CPU, as the CPU is also sharing the same RAM like a video. If we save the bandwidth from the video, it will be more left to the CPU. Do I see more questions? Theoretically, it's possible, yes. I actually at one place wanted to make it, and I forgot to do it. I need to convert it to the series of bitmaps, and on the same board like I have, I can show, yes, of course, I can show the slide, because this board has capability of show one complete screen on the one complete bitmap on the screen, and it has a memory to hold it all. It is possible, yeah. Maybe I will do for the next time. Yeah, this is a good idea, really. Okay, I don't see any more questions. Well, I guess.